Hello everyone. In this video I'm going to teach you how to give flexural reinforcement of continuous beam. So we are going to calculate the amount of steel required in a continuous beam. Okay. So for example, if we have a beam, so it's a continuous beam of two span A, B, C. Okay. And if we have calculated the moment already, so how we have calculated the moment, you can check other videos like moment distribution method, okay, any method. So let me just show you. If so, we know that the bending moment diagram is like this, right? So I'm taking, this is not simply supported. For example, if there is a frame, okay, so I have considered this part of the beam A, B, C. So your bending moment diagram will be something like that. Let me take some values of 369 kilonewton meter. So negative moment here, and here also 369 kilonewton meter, and here positive 369. Okay, let's look at these values and design for or calculate the amount of steel required for this beam. Okay, so I'm just considering beam AB, only this portion I'm going to consider. Okay, let us assume that the size of the beam is 300 mm cross, this is 600 mm. Okay, I'm assuming this beam size. So your overall depth is 600 mm, and let's take the effective depth. So 600 minus cover 30 mm minus, I'm taking, if we are having a stirrup, okay, there will be a stirrup also, and then there will be a bars. So the stirrup 8 mm I'm reducing, minus if there is another 20 mm, we can have two layers also, 20, and then because the effective depth is from the center of the reinforcement, so minus 20 by 2. So two layers of reinforcement I have taken. So if some bars are there of 20 mm dia of two layers, and then we have stirrup. Okay, this is what I'm assuming. So 30 mm clear cover minus 8 mm stirrups minus 20 dia, and then this. So this will be center of this bar. This is the effective depth. So we get 532 mm effective depth. Okay, now the moment is 369 kilonewton meter. For this we are going to design. So first let us check what is the capacity of this beam. Okay, so mu limit is equal to 0.138 FCK square. So I'm assuming M20 20 grade into 300 is the width of the beam we have considered, and our effective depth is 532 square. Okay, this is FCK we are assuming. So what is the value? 234.34 kilonewton meter. So this is, so this size of beam 300 cross 600 mm of M20 grade can take limit 234.34 kilonewton meter. So but our moment we have to design for 369 kilonewton meter. That means we have to go for, so this is less than mu, so we are going for doubly reinforced beam design. Okay, Otherwise, we could have designed as singly reinforced beam. So if you have referred the multi-story frame design that I have done, because the moment was less, so I went for singly reinforced beam, where like under reinforced beam I have designed. Okay, so coming to this, how it is to be designed doubly reinforced. So the concept of doubly reinforced is, first, this is the limit mu lim. For this, how much area of steel required? Let me put as area of steel 1. Okay, plus, that means steel in tension, plus so we have to design for mu. So our mu lim is 234.34 kilonewton meter. Let me put as mu1. Okay, and we have to design for 369 kilonewton meter. That means this has to be mu2 has to be 369 minus 234.34, so that this will be total. So this is equal to 134.66. So for this we have to provide the steel, area of steel 2 and compression reinforcement. Okay, so final area of steel at tension is area of steel plus 1 plus 2. So this will be at tension zone. Okay, and then this will be at compression zone. We have to provide. Okay, now so let's calculate AST1. So it is, this case is like your singly reinforced. So if your limit would have been less than this, directly you could have designed for as singly reinforced. So let me put mu1 is equal to 0.87 Fy into area of steel 1, okay, into D minus 0.42 XU. Okay, so your mu is given 234.34. So let me convert into Newton mm, is equal to 0.87 Fy. So let us assume Fe 415. We are using 415 into area of steel 1, which needs to be calculated. D is 532 effective depth minus 0.42. So your XU, you can directly put 0.48 D. Okay, because this is your mu limit. So XU max this is, which is 0.48 D. So this implies, so 0.48 D means 0.48 into 532. So only unknown is area of steel 1. So if we calculate, we will get 152.81 15282.1 mm square. Okay, now we know mu2, which is 134.66. So kilometer into 10 to the 6 Newton mm will get. So this is equal to, we have two formulas, one with respect to area of steel 2, another with respect to compression reinforcement. So let me calculate first area of steel 2. So area of steel 2 into, so the same, otherwise we'll put first 0.87 Fy into area of steel 2 into, here it will be D minus D dash. Okay, before it was D minus 0.42 XU. This was our lever arm, right? So now this is D minus D dash for the mu2. What is D dash? D dash is the effective depth, was the cover from the top, right? Similarly for the compression reinforcement, if we are providing, So d dash will be from here to the center of compression reinforcement. Okay, this is our d dash from the top to the where your bars are present, center of that. So your d dash will be same. We can provide like the 30 mm cover from top plus the stirrup size plus 2 bars I can provide. So it will be 68 mm. So this implies 134.66 10 plus 6 is equal to 0.87 Fy 415 into area of steel 2, which we need to calculate, depth 4 that minus 68. So your only unknown is area of steel 2, which comes 803.8 mm square. Okay. Now next is calculating the compression reinforcement. Same mu2, which is 134.66 10 to the 6, because area of steel 2, the here tension due to area of steel 2 should be equal to the compression due to ASC, the compression reinforcement we are providing. So same moment it will be is equal to the stress, which is FSC minus FCC into the reinforcement ASC in compression into the lever arm D minus D dash. So this is equal to, coming to the FSC, what is FSC value? So first for this, first you have to calculate D dash by D value. So that is 68 by 532, which comes 0.13. Okay. So for this D dash by D value, if you refer any book, you will get the value FSC is 344.75, which you have to interpolate Newton per mm square. So this value has come from the stress strain diagram. Okay. So stress strain diagram of the steel, they have calculated this value. So directly in tables for different D dash by D value you can get. Okay. So this FSC is the stress in compression reinforcement. So this is based on D dash by D value and your Fy. If in tables, if you refer, you will see for a corresponding value of Fy, which is Fe 415, and D dash by D value, you will get this FSC value. Any standard book, if you refer, and for any chapter of W reinforced beam, you can get these tables, which they have got from stress strain diagram. So 344.75 minus FCC. So FCC is the compressive stress in concrete at level of centroid of compression steel, which we are taking 0.45 of FCK. So 0.45 of FCK is M20 we have considered. So here the value is 9 Newton per mm square. So minus 9 into ASC we are going to calculate into 532 minus 68. Okay, so solving this, equation, the only unknown is ASC. So we are getting 864.4 mm square. Okay, so now, so ASC, how much we have got? It is 864.4 mm square, which is equal to, you can write 864 by 4 by BD, the area 300 into 532 into percentage of steel, if you need to calculate into 100, which is 1.46% of steel. Okay, area of steel, which is area of steel 1 plus area of steel 2. So total if we add, that means 1528.1 plus 803.8, you will get 233.1 mm square. So this is, if you divide, you will get 0.54%. Okay, this if you divide 8 by 300 into 532 into 100, you will get 1.46% of tensile steel. So this percentage of value, if you refer directly, if you refer SP 16 handbook, okay, standard book, standard practice 16. So Indian Standard Code, they also have this standard practice books where all solved examples, charts and tables are there to directly get the values. So if you refer SP 16 for doubly reinforced beam, for mu by BD square, so mu is 369 kilonewton meter, for which we are designing, by BD square this value, and your value D dash by D and FCK FY, they have tables where directly, if you refer the tables, so with respect to mu BD square, you will get the ASC and AST percentage. So this 0.54 and 1.46 percentage, you can also, here I have done whole calculation, you can also directly get these values referring the tables from SP16 also. Okay, that is also another option. Okay, directly you can get the value. Now coming to this compressive steel. So now our beam, if I am considering this AB beam, so our moment compression, the tension zone, because here it was minus, so here it was tension of minus 369, so we got the result minus 369 kilonewton here. For this, at the center we had plus 369. Okay, this is tension zone at this case. Next we have also at the right end same minus 369. Okay, so for this, how are we going to provide? So minus 369 means, so this whichever I have colored, this is the tension zone. Okay, that means here we have to provide the area of steel AST, which is AST1 plus AST2. That, so here we are going to provide how much steel? 1.46% here at top. Okay, and that means at supports, top we are providing 1.46% of steel, and at bottom we are going to provide 0.54% of steel. So here we are providing the tensile AST, and here we are providing the compressive steel. Similarly, at right end also we are going to provide area of steel here, which is 1.46% at top, and bottom we will provide 0.54%. But at center, okay, center, the tensile zone is at bottom, so here we will provide 1.46% and top 0.54%. So our compression zone is at top, and bottom we have tensile zone. So ASC will be provided at top and AST at bottom. So this is how you will be providing the amount of steel. That means if I am telling ASC is 1.46%, that which is 2331.8 mm square. So let me provide some 20 dia bar. Okay, so number of 20 dia bar, if I am providing, so number of bars will be 2331.8 by pi by 4 into 20 square. So you will get 231.8 by pi by 4 into 20 square. You are going to get 8 numbers. So you are going to provide 8 numbers of bars, okay, at top. So if, and at center means at bottom. So 2 layers of 4 bars you can provide. If I am going to draw this cross section, so you can provide 4 bars 20 dia in 2 layers. Okay, so I am just drawing this section near the support, which we have calculated. Similarly, you can calculate also for area of steel, which is 864.4 mm square. So you need 864.4 divided by pi by 4. So 864.4 divided by pi by 4 into 20 square. So you are getting 3. So if I am dividing 864.4 by pi by 4 into 20 square, I am getting 3 numbers of bar. So at tensile zone, 3 number of bars. So this section. So similarly, if I am going to cut a section here, so it is at top. So area of steel means bottom we are getting 8 numbers and top we are getting 4 numbers, 3 numbers. Okay. Top we are getting 3 numbers at center. This will be at center. This is at supports, your bars. Okay. So this is 420 dia, 820 dia and 320 dia. Here at top 320 dia and at bottom 820 dia. So this is how you can calculate the steel required in a continuous beam and provide the detailing. So your bars will be running, so top 8 and near the supports, and for bottoms 3 bars. Okay, so hope this was useful for you. Thank you for watching.